Okay, hi everyone. I know a lot of people had questions about optimization, so I figured I'd just make a couple of prompts and try them, and maybe I can give you guys examples. The idea of optimization is we're trying to either maximize or minimize um, our problem, and it's when we do optimization, it's we take the derivative of the equation we want to optimize. Now let's go ahead and see what this question says. A rancher wants to construct two identical rectangular corrals using 500 feet of fencing. The rancher decides to build them adjacent to each other so they share fencing on one side. What dimensions should the rancher use to construct each corral so that together they will enclose the largest possible area? Okay, let's give ourselves a little quick picture here. What this might look like. So we have a corral. Two corrals are adjacent to each other, so they share a common wall. We know that we're using 500 bit of fencing, so we'll call these y, 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 and maybe x and x, right? Okay, or so okay, so let's take a look. Or we could say we can even call this x, x, and x and x, right? So however you want to name it. The dimensions here. What dimensions should the rancher use to construct each corral? So I figure they mean these are the dimensions right here, right? Okay. So we know the amount of fence that we have for sure is 500, and this is gonna be made up of um, 1, 2, 3, 4, 4x's, 4x's, plus 3y's. Now, are we trying to maximize the amount of fence that we're using? No, we're trying to maximize the amount of area. So let's go ahead and come up with our area equation for this. Um, so area is equal to, I want to say we have 2 x times y, right? We're trying to maximize both these. Area of 1, which is base times height, or length times width, so x times y. And we have the other one, x times y, and we have 2 of them. Okay. So let's go ahead and we say we want to maximize. We want to maximize this guy here, and the way we learn this is we want to take the derivative and figure out where that critical point would be. So a prime, let's go a prime. Wait a minute, do you really want to take a derivative of x and y's? And that's the gimmick for most of these questions. You don't want to do two variables. So we're going to go ahead and get rid of one of these variables. And looking here, we can either solve for x or y. And it really doesn't matter in this case, because once we solve for one, we can solve for the other. So I'm going to go ahead and solve for y. So we're going to say 500 minus 4x all over 3 is equal to y. Okay? And then I'm going to plug this y into this problem here. So 2x times 500 minus 4x over 3. That's us finding the area with only one variable, x now. Okay, so we could take the derivative as it is. If not, you can simplify. If you want, you can simplify it. I don't think it hurts us to simplify, make it maybe a little bit. So it'll be 2 over 3. And I'm gonna go ahead and put the 5x in 500 x minus 4x squared. Okay, it's because I distributed x, but I kept the 2 on the outside, so it's a constant. So when we take the derivative of this, we still have our 2 over 3, which is our constant multiple. And we're going to go take the derivative inside, which is 500 minus 8x. Now when will this equal to 0? When 500 minus 8x equals to 0, we're going to go ahead and subtract 500 and then divide by negative 8. X equals to 500 over 8. We can reduce this to x equals to 125 over 2. Okay, so that's our x value. Okay, let's go ahead and find if I have my x. Well, let's see. Would this have given us a maximum? If we look at our a prime, we know we have a critical point at x equals to 125 over 2. Now, if I pick a bigger number than this, we can see that this is going to be negative, right? I mean negative. See, that's going to be a bigger number, so this whole problem will be negative. And if I pick a number that's, see, we have two possibilities, less than 125 over 2, our blue value up here again, right? That's going to be smaller, so 500 will be more positive. So our signs are going to go from positive to negative. So we have a maximum here. Okay, so let's go ahead and plug in, solve for y now. We have x, we have x, we have x, right? Oops. We have x, we want to solve for y. Let's go ahead and solve for y. We have the equation up here to solve for y already, right? That's up here is to solve for y. So y is equal to 500 minus 4x over 3. Our x value is 125 over 2. The 2 and the 4 divide out, leaving us a 2 and giving us a 250, right? 250. And 500 minus 250 is y is 250 over 3. And that's our dimensions. So what is the dimensions? Should the rancher use to construct each corral so that together they would enclose the largest possible area? That's it. They didn't actually ask us the area, the largest area, so we don't have to solve for area. We don't have to plug those in. And as you can tell, I didn't have to use a calculator for this problem. Okay. Let's go ahead and try the second problem. Oh, let's go try the second problem. This seems very similar to the first one. This time we're adjacent to, a farmer wants to construct a rectangular pig pen using 200 feet of fencing. The pen will be built next to an existing stone wall, so only 3 sides of fencing will be needed. So let's go and draw that picture. Next to a stone wall, this is my stone wall, right? Okay, so I don't need a fence there. And we're call this x, and y. So 200, that's how much fence we have. And we're going to use 2 x's and 1 y. Okay, and that's our formula that we have. We want to, then what dimensions will the farmer use to construct a pen with the largest possible area? Again, just like the previous one. So let's come with the area equation. A is equal to x times y. And we're going to try to maximize this guy, right? We're trying to maximize him. And when we want to maximize, we take the derivative. We're looking for a prime. But again, hey, we have x's and y's. So we don't want to take derivative of x's and y's. So let's go ahead and make our lives a little easier. And we're going to go ahead and solve for y here. Y is equal to 200 minus 2x. And we can plug that y in. So x times 200 minus 2x. And you could take the derivative of this, but I think it's easier to just write it as negative 2x squared plus 200x as we distribute that x over. And when I take the derivative, a prime, this will be negative 4x plus 200. Okay. Now this is how fast a prime is how much or at what rate the area is changing, is increasing or decreasing, and we want to find out when it has a critical point here. So let's go ahead and set that equal to 0. So 4x equals to negative 200. And then x equals to just 50, positive 50. And again, just to prove that this is a maximum, on the right side, if let's say pick 60, 70, 80, right? I could pick 60, 70, or 80. Let's pick 60. And we look at our derivative equation here. And if I did plug in 60, we're going to be more negative. Right, so more negative. If I plug in a number on my left side of 50, let's say 40, our derivative is now more positive, and you can tell the problem goes for a positive negative, so that's going to be a minimum maximum, a maximum, because we go from increasing to decreasing at that critical point. Now, in class, we've been working on concavity and our concavity test. So if we wanted to go ahead, instead of plugging in values, we could have taken the derivative again and find our a double prime. And that would give us negative 4. So if my concavity is negative and always negative, are we facing up or facing down? Downward facing concavity means that's negative, right? So our critical point 50, our only critical point here, is going to be a maximum. See, that's going to be a maximum, and that's us using our concavity test, which I think is actually even faster than us actually checking our slope. It takes up a lot of work for us to check this right here, but if we took our derivative, we automatically know that's going to be a maximum. Okay. All right, so if I find my x value, we have to find our y value. Lucky for us, again, we have our equation all ready to go up here. Y is equal to 200 minus 2x. X is 50, so 200 minus 100. X equals to, sorry, y is equal to 100. Okay, so our dimensions are 50 by 100. Okay, and don't forget to write feet. Okay, let's look at another problem. Okay, so this is a different type of problem completely. An architect is designing a composite window by attaching a semicircular window on top of a rectangular window. So the diameter of the top window is equal to and aligned with the width of the bottom window. If the architect wants the perimeter of the composite window to be 16 feet, what dimensions should the bottom window be in order to create a composite window with the largest area? Oh my goodness. Okay, so let's draw our picture. We have a semicircle on top with a rectangle on the bottom. We call this here the diameter, D, and we have some type of y value here from the height. And we're given some information. Let's take a look here. Oops. If the architect wants the perimeter of the composite window to be 16 feet, okay, so that means we are going to say that's going to be y, d, and remember this is half a circle, so the circumference is 2 pi r over 2. Right? So let's write that the perimeter is 16 feet, and this is equal to 2y plus a d plus a 2 pi r over 2. Okay, and let's write r in terms of d. R is equal to, 2r is equal to d, so d is equal to r, no, that's right. So r is equal to d over 2. We can plug that in, and we'll have 16 feet is equal to 2y plus d. Those go away, so plus pi d over 2. That's a pretty big equation. Our next idea is the area. Our area equation, this is a circle up here, right? That's a circle, and this over here is a rectangle. So let's create an equation for that. Area of half a circle is pi r squared over 2. The rectangle is base times height, which is d times y. Let's try that a little nicer. It's d times y. Now we have a lot of variables here, and we don't want so many variables. Maybe we can just write everything in d. So let's change some stuff. So we said before r squared can be r can be rewritten as d, so that's going to be rewritten as pi d over 2 squared over 2 plus d times y. Okay, my y value, it's up here, so we rewrite that as 16 minus d minus pi over 2d equals to y, all divided by 2. So it'll be 8 minus d over 2 minus pi over 4d. That's our y value. Looks a little messy. Okay, we know what y is now. Let's go and plug in the y. Open parentheses. 8 minus d over 2 minus pi over 4d. And then that's our a value. We can simplify this a little bit. So a is going to be pi over 8. 2 squared is 4. 4 divided by 2 is 8. We're left with the d squared there. Let's distribute this. It's going to be d or 8d minus 1 over 2 d squared. So d times d and d times all the way across. And we're going to be minus pi over 4 d squared. What some like terms here are d squareds and the pi. So we're going to take advantage of that. And we're going to go, that becomes a 2 here. And multiply that by 2, the common denominator, right? So it'll be 1 minus 2 is 1. So let's rewrite that as 8. Oh, that's going to go in order. Negative 1 over 2 d squared minus pi over 8 d squared plus 8d. We get that negative because up here, negative 2, and over here is a 1. Negative 2 plus 1 is a negative 1. Okay, that's my a value. So if I go ahead and take the derivative, a prime, because we're trying to optimize area, we're going to set this equal to 0. So the derivative of a is negative d minus, let's actually write it out for you guys. It's going to be, bring down the 2, so negative 1/2 times 2 d to the 2 minus 1 minus pi over 8 times 2. And then that's d to the 2 minus 1 plus 8 times 1. Because the derivative of d is just 1. So this simplifies to be negative d minus pi over 4 d plus 8 equals 0. We're trying to make this solve for 0. The trick with the d is I'm going to factor that out. And it's going to be negative 1 minus pi over 4 equals to negative 8. We divide it. D is equal to negative 8 over negative 1 minus pi over 4. Let's get rid of that negative and that 4. So multiply both sides by negative 4 on the top and bottom. And d is equal to 32 over 4 plus pi. And that's a d value. If we want to go ahead and find the y value now, we can use the equation up here. A little messy. Okay, let's solve for y now. Y is equal to 8 minus 1/2 of d, and we said d was 32 over 4 plus pi, minus pi over 4. And that's 32 over 4 plus pi is equal to y, right? We can multiply that out, but as you can see here, we have some common denominators that we need to mix. Let's use a common denominator of 4, right? We need a 4 there, and a 4 plus pi, 4 plus pi. So everyone gets to be 4 plus pi. So this guy needs an 8, 4 plus pi. Our second value needs a 2, so it's 64. Our last one, we are good, so it's just 32 pi. All over 4 and 4 plus pi. Top is 32 times 4. It's going to be a big number. 32 times 4 is 128. Plus 32 pi minus 64 minus 32 pi. Hey, these cancel out. These subtract out. 4 plus pi. We're left with 128 minus 64 is 64 over 4 plus pi. The 4's divide out, and it's 8. Not 8, I'm sorry. 16 over 4 plus pi. And that's our y value. So our dimensions are d, from diameter, and my y is 16 over 4 plus pi. So most of this stuff was actually the algebra 2. Almost everything here was algebra 2. Our only real calculus section was us taking the derivative here, right? That's taking the derivative, setting a equals to 0. And I think if we wanted to prove that this was a maximum, we could have drawn a sign chart, and we would realize this would go from a positive to a negative. Okay, there you go.